In this video, we'll explain how scientists capture light in space to produce pictures of planets, stars, and galaxies. To do this, we need to focus on the technology they use and how it processes light to create an image, which is very similar to how we take pictures on Earth. First though, we need to know a little bit more about light itself.
Visible light is just one of the types of radiation emitted by the sun, along with a whole spectrum of other electromagnetic radiation which is invisible to us. This radiation is commonly described as waves, but can also be thought of as particles, known as photons, that travel at the speed of light. Radiation is all around us, coming from a range of sources. Some of these are natural, such as rocks, bananas, and even your own body, and some are manufactured. A standard house lamp emits visible light, just like the sun. And when we want to cook popcorn, we use microwaves, which is another type of radiation produced as part of the sun's spectrum. When radiation is at low energy, it can pass through our bodies without us even knowing about it, such as radio waves from Wi-Fi. Infrared light, however, is also low energy, but can be felt by our skin as heat. It's emitted by any object that has a temperature, even cold ones like ice. However, radiation at high energy, such as X-rays, can cause harm to biological cells, so we have to be mindful of how much we're exposed to. To do this, we can measure it using a Geiger counter. As we travel up into space, away from the Earth, we experience higher doses of radiation that mostly comes from the sun. On Earth, we're protected from some of this radiation partly by our powerful magnetic field, which, along with our atmosphere and ozone layer, stops too much radiation reaching the surface, providing enough as a source of energy for plants to photosynthesize and allowing us to see things. Here on Earth, we've learnt to use visible light every time we take a picture. Early cameras relied on paper coated with light-sensitive chemicals that react to light to produce an image. The more light that falls in one region of the paper, the brighter that part of the image, and so gradually a picture can be built up. Modern digital cameras contain sensors that do the same thing, but instead of paper, they're made of materials like silicon that are also sensitive to light, specifically photons. These sensors are subdivided into pixels to make up the image. Within each pixel, photons generate electric charge, depending on the brightness of light. But when we try to take pictures in space, whilst we use radiation in the form of photons of visible light to make an image, other types of radiation can have detrimental effects on the performance of electrical equipment.
Much of space is a hostile environment, not only for us humans, but for the robotic spacecraft and equipment we've designed to explore for us. This is why scientists, like those at the Open University, test camera sensors that go on space missions to make sure they're capable of capturing accurate images of the planets and stars beyond Earth, to learn more about the universe we inhabit.
Inside every digital camera, amongst other electronics, there's an image sensor. The sensors commonly used in mobile phones are designed to be cheaply mass-produced, but they take good quality images in a wide variety of conditions. Yet this technology is not dissimilar to the sensors that we use in space cameras. The main difference being that the ones in space are capable of capturing much more light. We achieve this by making the sensors larger, much larger in some cases. This is the image sensor that was put into the iPhone 4S, which is very small in order to fit into devices that can be carried in your pocket. By contrast, this is one of the largest scientific image sensors being made for space applications. It has a similar number of pixels, but the pixels are much larger in order to capture more light. We use these vacuum chambers in the lab to simulate the space environment. Inside here, we can remove all of the air to create a vacuum, just like we find in space. We can also cool it down so that the sensors we test reach the temperature that they'll find themselves in space, which can be as cold as -120 degrees Celsius, much colder than your freezer, which is typically around -18. We then bombard the sensors with high energy radiation to measure how the image they produce degrades or gets worse as a result of this damage. Just like our skin in the sun, the longer a spacecraft is in the harsh radiation environment of space, the more damage it will experience. Therefore, the measurements that we take in the lab tell us about the corrections that need to be made to images that we take in space. If the camera we're using to film this now had been into space, we'd expect it to have been damaged by space radiation. If so, this is what I might look like on screen. You can see a few effects. Bright parts of the image are smeared over the dark parts, and you can see pixels that are bright or flickering. This is because of direct damage to the camera's sensor. Our research looks at how this damage is caused, how to best reverse these changes, and how to restore the image back to what's really there. You could imagine this is like removing the effects of a Snapchat lens to return the original unfiltered image. By understanding the processes that create this damage and therefore these effects, we can repair images once they're beamed back down to Earth from space. So what we end up with is an accurate image of what's really there. Here at the Open University, we work on image sensors that go on a range of space missions, some of which look back down at the Earth to learn more about things like climate change, and others that look at planets in our solar system or stars in distant galaxies to learn more about our universe. One of these missions, the European Space Agency's JUICE mission, is going to look at Jupiter and its many moons for signs of life.
The upcoming JUICE mission is going to investigate the icy moons of the planet Jupiter. One of the ways to learn about other worlds we know little about is to take pictures of them, allowing us to see all the features on their surfaces. But the radiation environment around Jupiter is exceptionally harsh, and this is in large part because of its strong magnetic field. It's roughly 20,000 times stronger than that of the Earth. It acts a bit like an enormous magnet that traps high energy radiation and makes it particularly challenging for spacecraft to function nearby. So we need to prepare any spacecraft and all of its scientific instruments, including cameras, as best as we can. One way of doing this is with shielding materials, sort of like putting on a hat to protect your head from direct sunlight. But we can't block out 100% of the radiation with a thick shield, as that would make the spacecraft far too heavy for one thing. And on top of that, we don't know exactly how much radiation is there in the first place. Yep, scientists don't know all the answers yet, and this is exactly why we send spacecraft to investigate. This means that when we send a camera into this environment, we need to check that it will perform in a variety of potentially very hostile conditions. This is what my research helps to do. In our labs at the Open University, we carried out a load of tests on the image sensors that are being used in the scientific camera on JUICE. Because of the unknowns surrounding the exact level of radiation around Jupiter, we had to subject them to higher levels of radiation than our calculations predict there will be, just in case. We then looked at our sensors and the data and images we get from them to figure out how much they've been damaged as a result. This information feeds directly into the JUICE mission to tell the other scientists and engineers how well the camera can hope to function in that environment. This knowledge can also be used to help correct images that JUICE returns to us, as Ben mentioned earlier. And even if they can't be corrected, it's important for scientists to know if some bright spot on an image returned from the camera is real, potentially signaling an exciting new scientific discovery on the surface of one of Jupiter's moons, or if it's simply the result of radiation damage. By digging deeper to understand how radiation can cause damage to image sensors, engineers can work towards designing new ones that are better at withstanding it.
important step in designing an image sensor for a space mission is in working out what scientists want to image and where in space they're planning to do it. Companies like Teledyne e2v, where I'm at in Chelmsford, work with space agencies around the world to meet their specific requirements for missions. Then they manufacture devices that are perfectly designed for the job. That could be for hundreds of small CubeSats looking back at Earth to learn more about our own planet and things like climate change, or a single detector for a space mission looking at another planet or a distant galaxy. I met with some of the team here to learn more. To test this equipment before it goes into space, we need a range of engineers from different backgrounds. Ian is a great example of one of these engineers at Teledyne e2v.
So the Open University conduct research and development into our sensors in timescales and in ways that we couldn't do as industry alone. So they enable us from their research to develop new technologies that we can build into future sensors to enable greater science in future space agency missions. My background is I graduated with a degree in maths and physics, and I wanted to work in an industry that would let me use those subjects and those skills in which I was interested. So I heard through some recruiting agencies about Teledyne e2v and some job openings there as a project engineer, so dealing with paperwork and testing and ensuring that the devices we wanted to sell to space agencies met the requirements and performed as they should. Over several years of doing that, I gained more expertise in diagnosing problems with potentially faulty sensors, and have used those skills to move into prototyping, so I can now test prototype designs that are unproven and demonstrate what works about them and what doesn't.
We need people with a range of skills to launch sensors into space, and people like Jude oversee the project as a whole to make sure that it's a success.
My role is managing projects within the business, whether that's customer-funded projects or research and development projects. My role fits hand in hand with a lot of the business functions that support the engineering in the back end of the business. Of course, we have our engineering and technician roles. We couldn't do what we do without them, but there's a big team of support functions that work in the background, managing projects, making sure our financials are there, and of course, speaking to our customers such as NASA, ESA, all of the big space agencies. We have to work with them to negotiate deals, make sure that what we're doing meets their specifications, and of course, that we're doing it to quality, on time, and to their budget. My favourite mission that Teledyne e2v has been involved with so far is the Rosetta mission, where our cameras were used to photograph the comet. It was particularly interesting because it was the first time we could really get a close-up image of a comet, and we've come out with some really high resolution photos that we've also been able to develop into 3D images that we can share with our customers and schools.
Engineers like Jerome need to understand how their research fits into the bigger picture and the steps along the way in order to get the mission to the launch pad.
Yes, therefore the relationship with Open University is very critical to us. We've got a very complementary relationship. We tend to work on the state-of-the-art technology to implement for missions, while the Open University work on technology that we will need in 5 years' time from now, before they are more in the research. We've got three test campaigns. One consists in submitting the detector or the sensors to the radiation environments via the laboratory that modelize and reproduce what's happening in space. The second aspect is to make sure that the device will age properly over the long mission, usually 8 years. In that case, we do a burning. That means we heat the device at very high temperature and we cycle it, and we see if the performance degrades or not. And the last one is to do some environmental tests, like shock and vibration, to make sure that they will resist to the launch and any harsh environment they might see following the mission.
We've seen how research scientists and those working in industry play an important role in shaping our understanding of space and the objects it contains. Launching rockets into space and equipping them to send us back data to answer the questions we have about our fascinating universe is a massive team effort. It takes years of planning and research even before a rocket is launched. We continue to need many different people from different backgrounds to enter the space industry, including those trained in science, maths and engineering, to design missions that will continue to push the boundaries and investigate deeper into space. We also need people to study the data and images being returned by missions that are active right now. In space, there is space for everyone, and that could be you, designing cameras for the next mission to the outer solar system, or studying faraway star systems that are being seen by humans for the first time.